All right, so my name is Adolfo Carvalho. I'll be talking about FU Ori objects, their outbursts, and how they can impact planet formation in this inner disk region. And one thing I'll be talking about the work that's made up the majority of my thesis, as well as and how I've been working to paint a clearer picture of the objects that actually undergo FU Ori outbursts and the conditions in the inner disk. So you've heard a little bit about So you've heard about accretion outbursts so far, but mostly in the relatively shorter-lived case and mostly in the lower amplitude case, as Agnes and Peter especially showed, and Michael Sessel's models were aimed at reproducing, and these happen over these. The sort of prototype of those is EX loopy, which shows outbursts with amplitudes of a couple of magnitudes in the visible, and they last maybe about a year or two. FU Ori outbursts are much more extreme. They are both brighter and hotter, and they are much longer lived, and they actually result in a fundamentally different picture of the inner disk. The outbursts observationally are identified as having these big 4 to 5 magnitude amplitude rises in visible wavelengths, and can last for several decades. Some we've identified as likely being an outburst for at least 100 years. And they have a variety of light curve shapes. As an example here, I've shown the light curves of the sort of 3 classic FU Ori objects. They were some of the first discovered. They are not the oldest or the longest lived. But this is a good representation of the diversity of their light curves. That tells us something about how the physics in the system is evolving, or the physical parameters of the system is evolving, but we're not totally certain how to interpret it yet. So to start with this sort of rough cartoon of the inner disk, and just to orient people, you've already seen some versions of this. Most of them much better than this, but I like that mine has actual numbers. And the numbers are informed by our VLTI friends and optical interferometry as well. And I'm really impressed that we can essentially see a lot of this region. Now I know there's some caveats. I know we're still working on it, but it's still impressive that we can get that close. But for reference, the star is about 2 solar radii typically. You go a few stellar radii out and you hit the magnetic truncation radius where the magnetosphere is able to withstand balances out the pressure from the accretion flow. Then there's some gas disk, the extent of which depends on the stellar type and stuff like that. You hit dust sublimation, then you have your dusty disk. During an FU Ori outburst, this picture is totally different. And that's because something destabilizes the disk. We don't know exactly where, though there's arguments that it should be at a few fractions of an AU or a couple of AU. Something destabilizes the disk, raises the accretion rate up to 10 to the minus 4 to 10 to the minus 5 solar masses per year, and brings the material crashing in. When it slams into the magnetosphere, the magnetic energy density is just not sufficient anymore to hold the material out. So instead of channeling material up to the pole of the star, you're now accreting directly on the equator of the star, and there is just no magnetosphere anymore. It threads the magnetic field in some complicated ways, but it's definitely not really contributing anymore to the accretion picture. The disk real quick also gets much hotter. So this T that I'm marking here is the effective temperature of the atmosphere that is established above the very hot midplane. But because of usually H- trapping, that region closest to the star can get up to tens of thousands of Kelvin. And so you end up with something that looks essentially like a stellar photosphere right next to your actual star. And it's the vertical structure of this we assume to be roughly similar to the radial structure of the stellar atmosphere. And that's at least how we were able to model them. And I've marked here for reference the peak of the rocky planet distribution roughly, as you've seen various versions of it so far. But, so this disk is experiencing really dramatic change in conditions, right where a lot of the various models we've seen today expect planets to be forming, and at around the same time when the star is less than a couple mega years old. We see these distinctly as absorption-dominated atmospheres because when the outburst happens, the luminosity is now about 100 times the solar luminosity. So all you're seeing is the disk and the absorption atmosphere of that disk. There's some emission that we see in like H alpha, but this is entirely because of the wind. And you see this is a blue shifted absorption line from the outflow compared to BP tau, which we've seen earlier in the week, which is a classical T-Tauri star that's accreting via the magnetospheric picture. The model that we adopt for these is that of a thin viscous accretion disk. There's a lot of assumptions here, but it's that mainly driven by the notion that you're converting gravitational energy to kinetic energy via heating, viscous heating, and the gas is in a Keplerian orbit. This immediately gives us a prescription from sorry, I'm missing a couple of citations here, I know, but this is basically the Shakura-Tsarnaev thin disk modified by Kenyon and et al. In 1988 to be isothermal as you approach the star, because in the Shakura-Tsarnaev disk you have a black hole, so the temperature can go to 0. We know it's not 0 near the star. But the main dependencies of these major parameters of the disk are that the accretion rate depends on this product of the stellar mass and the accretion. Sorry, the luminosity depends on the product of the stellar mass and the accretion rate divided by the inner radius. The maximum temperature in the disk has a similar dependence, but it's a little more more sensitive to the inner radius. And the maximum observed rotational broadening in the disk atmosphere goes as the square root of m over r, of course, because it's Keplerian, with the projection term from the inclination of the disk. So the question becomes, how do you constrain these things? Historically, when looking just at SED modeling, you can do a decent job of getting L accretion and T max, but because you have this degeneracy between m and m dot in the numerators of these terms, it becomes hard to actually get what the stellar mass is. So a relatively basic question like what mass of stars undergoes FU Ori outbursts is actually pretty unanswered right now. There are arguments that you can make for why you can have a certain limiting mass or something, but really the population is not actually known. And part of this is made difficult by the fact that the duration of the FU Ori outbursts means that we actually haven't ever seen one come back down. Okay, I have little time and a lot more to do. So the one thing I want to emphasize is despite how simple these models are, they do a really good job of matching the data, which gives us a lot of power to actually constrain these physical parameters. And the framework I've developed has brought us closer to understanding these. This framework relies on estimating the accretion luminosity via a new set of bolometric corrections I've computed. I have developed a technique that finds temperature-sensitive lines where these objects are spectroscopically bright to better constrain the maximum temperature in the disk, and as well as another way I'm working on to constrain the maximum temperature. And we use a cross-correlation function-based technique in the near-infrared to compute the maximum rotational broadening in the disks. When you pull all those, there's also the inclination that we rely on, and the inclination, AV, and distance are non-negligible, but we try to place independent constraints on those from other studies. The picture that we've gotten so far from the FU Ori objects that I've measured are that they are relatively low mass. They tend to actually have almost exactly the same maximum temperature object to object, regardless of accretion rate or stellar mass. Their accretion rate varies by about 2 decs, but the mass doubling times of the objects is actually in a much narrower range. And it's unclear why this should be, and I asked the theorists to potentially consider whether there is something in the mass doubling time that could be interesting to consider, but I don't know. But the outburst is really, really alters also the radiation environment of the disk in addition to the thermal environment. So during the burst, your FUV luminosity, which we found in FU Ori to be about 1/10 of the solar luminosity, which means it's about 50 times brighter than the FUV luminosity of typical classical T-Tauri stars. And the X-ray has been previously shown to be about 5 or 10 times brighter than typical classical T-Tauri stars. So the radiation environment is much harder. This is another version of that histogram of the existing planet distribution with data from the exoplanet archive, showing that as you have when you have this temperature increase, all the planets that, again, we've heard are predicted to essentially be forming there are exposed to these incredible conditions. You can also get much more rapid migration during the outburst because you get an increase in the local surface density. So you can rapidly migrate your planets, maybe producing an ultra-short period population or maybe eradicating your ultra-short period population, depending on the timing. And sorry, that sign is funny. The other thing that has recently come out, but is worth potentially considering, is that it turns out that heat, temperature, because you get up northward of the dust sublimation temperature, you can actually just sublimate away all your planetesimals that you've been forming. And some calculations by Juliet Becker and Konstantin Batygin show that it can be as effective as sublimating away Earth mass planets. So also potentially worth considering and modeling in more detail. But importantly, when you model these systems and even the impact on the outer disk and outer disk chemistry, the star just doesn't matter. You really need to be considering what the radiation field is in that inner disk if you want to do detailed chemistry and stuff like that for outbursting sources, especially FU Ori sources. So I'll leave up my summary and open up to questions. Thank you.
Richard Nelson, Queen Mary, University of London. Thanks for a very nice talk. A couple of questions. Don't think you mentioned the ages of these systems. Do we have good age estimates? And also, what about disk masses as well? Do we have estimates of disk masses?
We don't really have estimates of ages. We have some good estimates of disk masses from a handful of millimeter studies of the objects, including a great one led by Agnes. The disk to stellar mass ratios, taking my stellar masses and the millimeter disk masses, can be are as much as 30%. 30 to 50%. They're enormously massive disks. Based on the fact that they seem to be extremely massive and a lot of these tend to be quite embedded, they're likely younger than a couple of mega years. But we can't do much better than that.
Great. Thank you so much. Thank you.
Hello, Arturo, UNLV. I wanted to ask, you show the last part where you toss the planets away. And you show Earth mass types planets. What about a gas giant who are probably the ones that are more in this area migrating rapidly? Would you expect them to fall into the star, or are they going to be stripped of their atmospheres?
Yeah, so a couple of years ago there was a paper showing extreme evaporation of massive planets is possible during these outbursts, and in fact it was even invoking that as a means of providing a mass reservoir to feed the long-lived outbursts. So the picture would be you have EX loop type bursts going off every few years. You get one that just happens to be bright enough to trigger extreme evaporation of an unlikely Jovian mass body, and then that extreme evaporation can actually feed the outburst as it goes on. Unclear if that's the case. We don't really see precursor outbursts to the actual FU Orionis event, at least for the ones we've detected. So unclear if that's what's happening, but it is something that has been considered.
Thank you.
Bennett Skinner, McMaster University. Would we have any observational signature of these planet destruction events?
So there are some potential signatures. One of them that's pretty immediate to predict is a metallicity increase as a function of time in the spectrum that you observe. The trouble with that is that metallicity sensitive lines are The ones that are really metallicity sensitive are somewhat few and far between, and for the amount of mass that you would be putting into the disk. And the rotational broadening of these is tens of kilometers per second, so you blend sensitive lines into insensitive lines, and it becomes very difficult to actually tell. What we do see is outflows that seem to have a lot of iron and titanium at low velocities that are presumably probing near the launch point of the wind. So maybe you're seeing some iron and titanium getting populated into the wind or something. But
thank you.
Okay, great. And one more question.
Hi, Michael Zettel, MPIA. So you showed in the beginning that if the accretion rate is very high, then the magnetospheric accretion process ceases to work and you get this boundary layer accretion.
Yes.
So do you consider this in the models yourself? And if so, how do you then set the R inner, so the inner radius of the disk that you need in your equations?
Yeah, thank you. So we don't, to simply answer it directly, we don't consider a boundary layer per se. The models are relatively simple. We take a temperature profile and put in a pre-computed stellar atmosphere at the appropriate effective temperature as a function of radius, and then integrate that to get the disk spectrum. Our inner is something that we actually allow to be independent because we don't always have very good constraints on the pre-outburst object. So we actually have to infer all of the stellar properties from that. So sometimes it requires assuming that the stellar radius is about where the disk truncates, but that's not always the case. And in fact, a couple of years ago, I published a result for the object V960 MON that showed that it actually that inner radius seems to be receding as the accretion rate in the system decreases, consistent with potentially the magnetosphere reestablishing itself. So it's still sort of up in the air there, but there's we're still working to study what the boundary layer exactly is.
Okay, thank you.
Okay, great. Well, let's thank Adolfo for a great talk.